Hello everyone. Good evening. Uh, Today we'll have a discussion on week 4. Hmm. Yes, Barendra Bal.
Sir, I had a question regarding not the content of week 4, but the coding questions that we have the private test on them. So
Uh,
when
Test
they
case. You mean test cases?
yes, private test cases.
Oh, which
When
question?
the
Question number?
not in particular, I'm just
Oh, okay,
saying.
okay.
So when they don't pass, we don't
Hmm.
get any kind of feedback. Is it kind of stack overflow or is it passing out of time? So it would be
In
helpful.
TLE, you don't get any kind of feedback about TLE. Means definitely there will be a TLE error. Anyone also face this issue that they are not getting uh, any feedback kind of thing, yeah, or any error raised, like what he is saying?
Sir, I don't think there is a time limit exceeded feedback for private cases. For public cases, there is.
Because we have implemented in such a way that TLE should raised.
I have faced this problem too, like before.
I
Like
mean,
for
in week 2, we had a
yeah,
problem about that, kind of binary
binary search,
searching
rotate, yeah.
problem. So I didn't know why I was only passing one case instead of two. It turned out I was using, I coded using recursion and, using recursion. So that's why it was going over time limit. If I coded using, non-recursively, then it would have passed.
Okay.
That
What you are saying?
I was saying that was because of we were using the slicing of list in the array that was taking more time.
No, uh, the way I solved it was correct, but I was using recursion, so that's why it was taking more time. If
Yeah, I also
yeah,
used recursion. That's why I'm saying.
yes.
So I want to know more. Means you are uh, solving a problem and your test case, suppose test case are not passing. Okay,
Yes, going
so
over to
you
the
are
time limit.
okay, so you are not getting any kind of raising error kind of thing, like statement or something that this kind of error is raising, right?
No,
Like
sir.
uh, so uh,
The
TLE
private
kind of
test
thing.
cases, yeah.
Oh, means you want uh, any kind of, means you want some kind of feedback, right? That this
Yes,
is
that
the
would have
error,
been
pointed out
helpful.
that this is the error,
Yeah.
or stack overflow, or means something like memory overflow, these kind of thing.
Yes.
Yeah,
Sir,
so
even a
something like
simple
that.
runtime error
Just to
would be good.
understand what should I change in my code. Should I optimize more or implement in different way? Just to understand that.
Okay, actually, what we have done in uh, while coding this problem, we usually uh, we don't do this kind of thing. uh, I'm talking about myself. We don't do but as far as I know, TLE was implemented, and but why it should not come?
TLE comes if it fails public cases.
Yes,
Oh,
not in private cases.
okay,
Only in
okay.
private cases, and I think the question key objective is whether you don't want us to know what those test cases are at all, because technically if you show us the error of a private case, then we can always write an output and find out what the input is. So I think if your objective is not to allow us
No, I'm
find out
not
what those
asking
test
for
cases
the
are.
exact error. I'm just asking,
Hmm.
I mean, is it kind of
Actually,
runtime error,
yes,
or is
yes,
it going over
yeah,
time?
yes, you are
Just that
right.
much.
We didn't implement this kind of raising error statement like runtime error or something, but TLE, but I need to check with our team member. Uh, so uh, yeah, this kind of things we didn't implement generally in coding. Okay, okay, I'll talk with them that,
Okay, sir.
but for for the coming assignments like week 5 or week 6, uh, yeah, we cannot do much on these topics like raising error issue, but
Okay.
we'll try to implement in other assignment. Okay, any other issues? I want to know where are you from? Means all of you, mainly uh, which belt? All of you means.
I'm from West Bengal.
Okay, means uh,
Sir, I am also from West Bengal.
okay.
Sir,
I'm from
Mumbai.
Maharashtra, Aurangabad,
Sir,
Maharashtra.
Mumbai,
Kerala.
sir.
Delhi.
Okay, okay. Snehil.
Bihar.
Okay, okay. No, okay, okay. Just got okay. Uh, Actually, Snehil, we are discussing about the week 4 issues. Uh, uh, about the older PPA, what I will suggest you that keep your questions ready, and we'll have a next week, we'll have a revision session. Not for all the 3 assignments, means not all the 3 session. We'll have a week 5 session also, but in the live coding section, where we do live coding, there will be, I think there will be a revision session, so you can ask your question, uh, older PPA's question, in those revision session, because we will have a quiz coming, and quiz syllabus is, from week 1 to week 4, so you can ask
But
there.
sir, the live coding thing is on Saturday. So I mean, just the day before quiz, it will be, I mean, a bit messy.
Mm, maybe yes, maybe not the Saturday, maybe we can have a session before this, means Thursday or Wednesday. We didn't sure about this when can we have, but there surely in the next week we'll have one revision session for all the weeks, from week 1 to week 4, I think, along with week 5.
Sir, maybe on this Saturday also we can have a small revision session.
This Saturday, but if we allow Saturday session as a revision session, then what will be a week 4 live coding? Live coding is also important because week 4 is coming in your quiz.
Yes, sir. Maybe half an hour only, sir. Then revision.
uh, I don't know actually what is the plan. I don't know about the plan, but next week surely we'll have a one revision session. but this week uh, I don't know about this week.
So can we
Sir,
discuss
for
some
half an
topics,
hour.
please? Like
Okay.
week 4 topics.
So can we discuss a question from week 3 graded assignment?
We can discuss in revision session, okay, about week 1, week 2, week 3. So right now we will discuss about week 4.
Okay, sir.
So it
Yes.
would be helpful if we could discuss like DFS numbering once, because there are some doubts.
Okay, we'll discuss. Yeah, ask.
Yeah, like mainly I have doubts in back edges, how DFS numbering can detect back edges. Like it would be helpful if you could discuss the
I'll
entire
tell
topic
you.
once.
Yes, I'll tell you. DFS. Okay. Okay. Yeah, I'm going through the slides. Okay, wait.
Excuse me, sir. I have a general doubt in directed graphs and undirected graphs. Can I ask?
We'll take your doubt after this DFS numbering. Okay. Hello, can you tell me in which slide we were doing the DFS with numbering? So I can share that slide and we'll discuss there.
It was in applications of DFS and BFS, right?
Okay.
Page number 30.
Yeah, can you see my screen?
Yes, sir.
Yeah, DFS tree and all. So, what is your doubt regarding this numbering, means backtracking, pre and post? I think post numbering, right?
Sir, it would be helpful like if you could explain the whole concept and focus on back edges, how back edges can be detected more.
So, here we are just starting, just taking zero as a zero as any, means we can choose any vertex, right? So zero is the vertex and zero is a just we are just counting, and every time we will, what sir said, every time we'll increment our counter whenever we just visit any vertex. So there is a zero vertex and zero okay, counter is zero. So we can visit 1 and 4. So here what we visited here, we can visit, so we have chosen 1. So what we have incremented, we incremented our counter as 1. Whenever we visit, we will just increment our counter, increment. Yeah, it's written also that increment counter each time we start and finish exploring a node. Okay, so we'll increment every time we just explore any vertex, and we'll increment our counter also. So here, because it's a depth first search, so because we have visited 1, so we incremented our one as a counter. Okay, so what we can do, uh, as you know, after going from 0 to 1, we do not have any vertex where we can move. From 1 we cannot move any of the vertex. So this is kind of a stopping kind of thing. Yeah, we stopped there. So what we can do, this is a post increment counter, right? This is a post, so we are incrementing 1 was pre and post as a 2, because move we cannot move from here to any other vertex. So we are just,
Excuse me.
yes.
Sir, actually, sir, before this, if you could like slightly explain, what we are trying to achieve and why, this pre and post would be helpful. I think we will grasp it better.
uh, Here we are.
And maybe could you code alongside, like if you would code, we would get a clearer picture on how to execute
code
the
alongside.
code while doing the logic.
So let's go one step at a one question at a time. So for the question which someone asked, like, what is this? Why are we using this pre and post? Can you answer that?
So what I'm saying, code is sir explained a code very brief, means for this one sir has already coded, so you can go through the videos also. There sir explained the code, so I don't think we need the code along with this explanation, uh, because sir already mentioned about the code and all.
Okay, sir, no problem.
No, sir, but
uh,
some motivation behind the topic would be nice, like if you could give.
yeah, in the video itself, whenever I don't know how much you have spend your time in this lecture, but sir
Yeah, sir
already.
has said that we can use DFS numbering to detect cycles.
So this is the reason, because you know that application of BFS and DFS, this is application, and we know about DFS and BFS. Okay, I'm assuming we know about BFS and DFS, it's working, and this is application. So what we can do here, we are trying to detect cycles. Okay, so that's why the numbering came. We want to know, suppose like here, uh, actually, uh, by seeing the graph like 0, 1, 4, 8, 9, we can know that 489 is a cycle. But how computer thinks, means how algorithm thinks that we already visited 4 or not, means for cycle, starting vertex and end vertex should be same, then there will be a cycle, so by seeing the graph we can know. But by the algorithm, how do we know that we have already visited the node itself? So that's why BFS and DFS, we are using here BFS and DFS algorithm to detect cycle. Like, we want to know the visited we have, because you know, in the BFS we marked, we explore any vertex and then we mark vertex as visited or not visited. If visited, then we include in our queue. So this is kind of the algorithm, like be in the BFS we generally do this. Okay, first we will explore the vertex and then we'll, if it is not visited, then we mark as a visited and then we'll include in the queue. So by this way, we can know that, yeah, this vertex, we know that, yeah, we have already visited this vertex, like 0 is already visited, so we know that 0 is already visited vertex. So by this way we know about these vertex. So by we have a information about any vertex visited or not visited. So by this way we can detect cycle in a graph. Okay, so this way.
So, like, let's say I'm doing my DFS thing and I have a visited dictionary. So, while doing DFS, if I encounter a node which was already true, marked true, then there is a cycle.
Yes, if it is undirected. In directed graph, we have to know some other information also, because but indirect, but if it is undirected, then we can know that, yeah, if we visited, uh, if we use DFS, and because in DFS we generally back propagate also. We apart from visiting any vertex, we do back propagation. Generally we go backward also. So uh, for these things we use numbering here, I think. Okay, let me check here the numbering concept.
Sir, in directed graph, can we use DFS to calculate shortest path?
uh, Directed graph.
Yes, sir.
Sort, yes, we generally do uh, DFS and we generally use BFS and DFS to detect
So I think if the graph is connected, then definitely we can use.
shortest path. For shortest path, this is the algorithm we generally use, BFS and DFS both.
Sir, can you explain this how we can use both? Because I'm getting confused in case of directed graph. Because what if the edge is not reachable from source to destination, then how we are
If it is
supposed to?
connected, if it is not connected, then how can we apply any BFS or DFS algorithm, right? If
No
uh,
connection, but
Sir,
graphs
I
are
think
directed. Graphs
BFS we
are
cannot do, I think BFS with the
for
BFS.
for shortest path only VFS can be used. I think so.
Huh.
Because
For if it is connected, then BFS can be used.
sir, for directed graph, I'm asking, and not for undirected. So my question is, if it's a directed graph, every is connected. But still, how we can ensure that it's the shortest path again?
So by using levels, we can also find the minimum, shortest path.
But then can we keep the track of the shortest path too in BFS?
if we are going level by level, that means we are actually using BFS, right?
But it's a directed graph again.
Yeah, if it is a directed graph, it is connected and every point is reachable from like every other point, then we can use BFS there, right?
But then, yeah, we can ensure we can give level, but how we can ensure it's the shortest path?
You discuss, I'm just focusing on the numbering.
You are
Okay,
right, Ishan, but BFS itself ensures that we are going to calculate shortest path.
Depend upon the
Can we calculate the
vertex,
shortest
from
path?
which vertex you are finding.
Yeah, right.
Sir, a humble request to you. If you can just give a recap or brief up about BFS and DFS and then go ahead with coding part so that everybody will be getting clear about that BFS and DFS concepts.
I think that's a good suggestion. Yeah.
Yes, sir. And you also won't have to go through the slides again and again.
Okay. Okay. I'm just giving you a brief, right? So what we do in BFS, like if we suppose we have a connected kind of thing, like we are considering 2 3 6 7 10 11. Okay, so what we do in BFS, we just select any vertex. So here we are selecting vertex 2. Okay, so when we select any vertex 2, so what we can do is we have a choice that what we can select. So BFS, you know that we have a label. We generally do in labeling, means in the label first level, we will traverse first level, then we traverse the second level, then third, then fourth. So we visit all the neighbor vertices. So we have a neighboring vertices 3 6 and 7. So we what we can do, we just explore 3 6 7 and check it's visited or not. If it's not visited, then what we can do, we can insert them in a queue. You know, queue is sir explained about that. Queue is a first in first out kind of thing. It's like a uh, you know that open drum, open pipe, you can say that open pipe, horizontal open pipe you can consider. So uh, what we can do, we insert 3 6 7. Okay, because we are and already we have visited, we have marked as a visited. So 3 6 7, we inserted 3 6 7, and we will pop out just, we will just pop out 2. Means what we have done, we just deleting 2 from the pipe, and we inserted 3 6 and 7. So uh, what we can do here now, that we will pick 3. And so because 3 is inserted first, so 3 6 7, so we'll pick 3. And then what we can do, okay, no, it's not LIFO. LIFO is stack. Okay.
So, sir, stack is used internally in DFS, right?
Yes, in DFS. In BFS, we use queue. So I'm discussing. So you do not.
Sir, we use queue in BFS.
Yes, and I am discussing about BFS.
Sir,
But
BFS
this
or
is
DFS?
DFS, right?
It's getting confused.
No, I am just discussing about the BFS. Yeah, I am just considering this as an example about BFS. Understood?
Yeah, okay.
Yeah, I am just taking this 2 3 6 7 10 11 as an example of BFS, how BFS is working. So I am talking about BFS, not DFS. So in BFS, we inserted 2, and we check that what is the neighboring vertices 3 6 7. So we'll pop out 2, and we'll just check about the 3, that neighboring vertices of 3. So neighboring vertices, you know that 2 and 7, and these are all already marked as a visited. So we do not need to insert 2 and 7. So what we can do, will pop out 3, will pop out 3, and then what we can do, will go to the 6. Okay, so we have a 6. So what is the neighboring vertices? 2 already marked as a visited, 7 already marked as a visited because we already inserted it in the queue. So 10, now the 10 is left, only the thing we left. So we what we can do, we mark as a visited, and we will insert 10 in the queue. So now 2 3 has been done, 6 has been done. Okay, we have inserted and will pop out 6, and we have inserted 10 in the queue. So now we have a 7 and 10. So we'll pop out 7 now and then check that what is the neighboring vertices. 3, 6 and 11. So 3 already visited, 6 already visited, and 11 already, no, 11 is not visited. So we'll mark 11 as a visited and we'll insert it in the queue. Okay, so now we can go to 10. Yeah, 10 we have, and 10 already, 6 and 7 already visited, so we don't need to explore any other vertices. So we'll go to 11, and 11 we already know that 7 is only vertices, neighboring vertices already visited, so we'll pop out 11. So by this way we have explored all the vertices. Yeah, right. So understood about BFS, how BFS is working.
Sir, here actually the doubt is that after 15, 16, somehow we have gone to 11, like after 6, whereas there is no connection between 6 and 11. So from 6, we should have gone to 7, and then via 7, we should have come to 11. But if you see the numbering, from 16, we have gone to 17, which is marked at 11.
16, 11. Sorry, where in this section you are talking about?
Priyanka sir
yes,
is
sir.
discussing BFS, not DFS actually.
Actually, I am just taking it as an example, and this is the numbering. Here I will complete this because we okay, after DFS will complete. So this is, I'm just taking 2 3 6 7 10 11 as an example of BFS because we so is it right?
Yeah. Sir, when do we know ki our this traverse completion is over? When the stack is
Queue is
empty, right?
empty. Queue is empty.
Yeah, sorry,
Yes.
stack queue is empty, right?
Yes. So by this way, we can traverse all the vertices 2, 3, 6, 7, 10, 11. This, consider this as an example. So and time complexity, regarding time complexity, you know that we have a two uh, we have uh, we have two way to do this. One is adjacency matrix and one is adjacency list. And you know that in adjacency matrix, what we are doing, we
No,
have
sir. For the time complexity discussion, if you can open the side by side the code and then you discuss the time complexity, it will be helpful, sir.
Okay. So I think sir already, I'm just briefing about the BFS and DFS. Sir already taught us about by the code also. Sir has taught us. So I don't think we need this. I'm just briefing about how, what you can see there in the code in the video also. Sir
No, it is
already.
there, but you are discussing time complexity. That is why I'm saying.
Yeah,
It will
I'll
be
tell you.
easy.
Okay, I'll tell you about the time. Means I'm just, by this way I can also tell you. Suppose we have n vertices. Okay, and we know that we have adjacency matrix. Okay, so what we are doing, we are just first exploring the vertices. Means time, how we will calculate uh, time complexity, means what we are doing. So in, suppose we have n vertices, so we are just first exploring all the vertices. So by exploring means we are just marking as a non-visited, 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 because first we can do that 2 3 6 7 10 11. We have a code also. Okay, if you want this, here is a code, I think. Suppose here what we are doing, for I in a list dot key is visited, I is equal to false. So by this way, what we are doing, we are just what we are doing, we are just exploring all the vertices as a false or non-visited. Do not take this code as a time complexity. I'm just giving you example, like we are just marking as a non-visited every vertex as a non-visited. So by exploring, we are just calculating, we are just doing in order of n, because we are exploring all the vertices. So this is order of n, and for n vertices in the adjacency matrix, what we do in adjacency matrix, you know that we have kind of 0 1 2 3 4 5 some vertices in row and some vertices in column. And what we can do, there is a 1 and 0 kind of thing. 1 means there is an edge and 0 means there is not an edge. This is adjacency matrix. So uh, so by visiting, now we are just visiting n times. Every vertices we are visiting for every other vertices. In worst case, I am just talking about, you take my word as in worst case, for every vertex, we have to visit all the vertices in worst case scenario. So for that's why by exploring n times, and for exploring n times, and for doing for taking one vertices as a source vertices, and we are just going through all the vertices. You know, in the adjacency matrix for 0 we have all the vertices. uh, Understood or not? Means, you know that for 0 means, suppose 0 is a vertices or 2 is a vertices, we have to check all the vertices. There is a 0 and 1 kind of thing in adjacency matrix, right? So everybody is getting my point, what I am trying to say. So we have to visit all the vertices. That's why n into n comes. So that's why this is order of n square when we will use adjacency matrix. And you know, in the adjacency list, we have to visit, we do not need to visit the vertex which the older earlier vertex have not direct connection with that. Okay, means earlier in the adjacency matrix, we have to visit all the vertices which are not connected to that vertices. But now we will visit those vertex, only those vertex which has a direct connection, like which have only once there. Okay, so suppose for 2, we just have to visit 3 7 and 6, only this. So and uh, sir explained about for every edge we have a 2 vertices, right? For it includes 2 things for every edge. Suppose this is, we have a 2 and 6, for this is we have a 2 and 7. So for every edge we can have maximum 2 vertices. Okay, so in the adjacency list, what we are doing, what we are just going through all the edges, order of n, for exploring the vertex. And for doing for every edges, we are just exploring, means we are just marking, or maybe we can say that we are going through every vertex. For every edges we can have at most 2 vertex. So by this way, it can be a maximum 2m times, means 2m times. Sir was saying that m is a number of edges, so 2m can be, we can do only 2m, maximum 2m. Because for this, suppose we have a 1 2 3 4 5 here, 6 7 8. So maximum to maximum we can have 16. 8 into 2 means we can have 16 vertex, means we can visit 16 vertex. So here we can say that we are seeing that 2 3 6 7 10 11, just 6 vertices, but maximum we can go to 16. So it can be covered in the worst cases. So for every edge, we are just taking two exploring vertices. So we are contributing. What we are doing, we are not going through all the 3, 6, 7, 10, 11. We are just going to 2. If we are taking 2, so we are just going to 3, 6 and 7, only this. If we are taking 6, so we are just taking 7 to 10. But earlier we were going to 2, 3, 7, 11, 10. We are visiting all the vertices. That's why the time complexity was n square. Now the time complexity will be n something, n number of vertices, uh, and edges twice the number of edges, maximum to maximum twice the number of edges in the worst case scenario if we use adjacency list. So this is the time complexity of breadth first search. Similarly in DFS also, what we can do here, you know that DFS is kind of thing like it is going through vertex to vertex every time. So here DFS we can use stack. Okay, it's kind of LIFO. So here, like we are just going through vertex, then vertex. So we suppose we are taking 2 as our initial vertex. We can mark them as a visited, and we will insert into the stack. So we can visit 3, 6, 7, anything we can visit. So if we visit 3, so we have 7, we can have only 7. Okay, we can have only 7 here. So we will just visit 7, we will insert into the stack, we will have 7. But here we have 6 and 2. 2 is already visited, 3 is already visited, 6 is there, so we will insert 6. So the difference is here we are not going through all the neighboring. Like earlier in the BFS we were inserting 3, 6, 7 all together for 2, but now here we are not inserting all the 3, 6, 7. We are just inserting it one by one. 2 after 2 we are just inserting in 3. After that we are just inserting 7. 7 we have 2, 6, 3, 11. So we are just inserting, we are just choosing 6, so we have a 6. So after that we cannot insert 2, 7 because it's already visited. So here we are visiting 10. 10 after, then we are just stuck here. There is a kind of thing stuck, like 6 and 7 already visited. So what we can do here, you know that 10 understood, 10 here after reaching the 10 we cannot go to 11. 11 is unvisited and we cannot go to 11, and there is no way from 10 to 11. So what we can do, we will backtrack. So after 10 we will backtrack to 6, and after 6, yeah, we know that already visited, all the vertex are already visited, so we will backtrack to 7. Now 7, we we think we sees that 2, 3, 6, 10 all are already visited, only 11 are unvisited vertex, so we will go to 11 also. So there it ends, means it, we reached the state where all the vertices uh, is visited. Okay, so this is the process of DFS.
Okay, sir. Understood. Sir, one query. So in DFS, time complexity was, in worst case, the time complexity was n square. But when we are considering the integers and taking all the edges, so maximum 2 integers can be placed in that 2 edge. In one edge, we can place 2 integers maximum.
Yes,
So the worst case, the time complexity will be 2 into m, right?
yes.
Okay. So it won't be n square.
No, what in the DFS also, uh, there is two way. One is adjacent, one is calculating by the adjacency matrix, and one is calculating by adjacency list. So in the worst, both are the worst case. In when we are using adjacency matrix, so what we have understood from BFS, the same applied here. We will have order of n square time complexity in worst case. Okay, and in the worst case, when we use uh, adjacency list means for 2 there will be a list 376, for 3 there will be a list 72, means all only connection, only means connected, directed connected edges.
So this is the form of calculating time complexity in the form of adjacency list.
Yes, adjacency list and adjacency matrix. So
Both are same.
no, both are not same.
So you are approaching for list part, right?
Yes, both are not same. These are the ways we will calculate the time complexity. uh, One for from one way we are just getting maximum time complexity big O of n square, which is large enough, and for the second one we are using adjacency list, so we are getting linear time complexity like order of n plus 2m. M is number of edges. So it will help us to reduce the time complexity. So these are the ways. Okay, the BFS and DFS. Coming to the numbering of the BFS and DFS. DFS.
Sir,
Yes.
uh, uh, before going to the further topic, I have a doubt regarding the calculating number of vertices from edges and number of edges from the vertices, whether it is maximum vertices or minimum vertices. So that kind of calculation, I mean, if you can explain, please.
Maximum number of means
So
the
suppose number of
degree.
suppose a minimum number of vertices from certain edges.
Minimum number of vertices.
Suppose in a connected graph, say a number of edges has been given.
Suppose,
So
yeah, you can take this example 2, 3, 6, 7, 10,
yes,
11.
yes.
Okay.
So say a number of edges has been given. So this case, the number of edges is 3, 3, 6, 8. So in that case, if the number of edges is 8, so what should be the minimum number of vertices? I mean, how should we approach to calculate this kind of? I mean,
Okay. Means actually this is a pure graph kind of question. uh, Purely graph theory question. uh, uh, this kind of question, I don't know I'm exact or not, but this kind of question can be done by this way, that for every for we can know that for every vertex we can have
just like Sir has mentioned, say number of for a connected graphs, number of edges minimum is n minus 1 and maximum is n into n minus 1 by 2.
By 2, yes.
Correct. So this is the minimum and maximum limit he has explained. And also he has explained the sum of the total degree of the whole node is the 2m. Correct. So this must, I mean, details has been explained in this, I mean, particular videos. But as we have gone through the all kind of calculation in the maths part, but we have forgotten. Just that's why we are asking. I mean, if you can explain how we should.
Actually, yeah, I can approach to your solution. I can give your approach, my approach, but you have to ask a particular question. about the because it is related to the graph theory, right? So you have to ask me particular question. You I don't understand what you are trying to say, that minimum number of vertices for that for certain ages. So I didn't get the uh, exact intention.
Okay, I mean, there is a question in the graded assignment, but we don't want the solution, but we want to know the approach. I mean, there is, I think, some, I mean, determining the minimum number of vertices from certain age.
So which question? Yeah, tell me exact kind, right? Exact question. So I'll help you.
Fine, I need 1 minute, then I am coming.
Yes. After this, we'll come to the numbering section. I remember that DFS numbering.
Question number 7, sir.
Hello. You can type. Okay, okay.
Sir? Sir, am I audible?
Yeah, you're audible. Yeah.
In the graded assignment 10, there is a question, say, an undirected graph G has 17 vertices. The sum of the degree of all the vertices G in G is D, and the number of vertices of even degree is in G is K. Which of these values are possible for the D and K? So, I mean, just to calculate this kind of number of vertices and the degrees, if you can explain bit.
Okay, okay. I will explain you. So here given undirected graph G has 17, sorry.
Yeah.
And sum of the degree of all the vertices in G is D. Okay. The number of vertices of even degree in G is K. Which of these values are possible for D and K? Okay. Okay. So you know that sum of the degree of all the vertices. Okay, sum of the degree. It says that the sum of the degree of all vertices in
It
G
is
is D.
2m. It is 2m.
2m. So
Yeah.
you know that 2m. So if it is 2m, then it should be an even number. So
Correct.
Right. So
Correct.
by this way you can know the answer, like it can be even number, not the odd number, right?
Okay.
So actually I'm telling the answer. So you know, right, this is the D. It means D can be a even number, not the odd. Okay, so this is the, by this way we can know that because for vertices, because we just only given vertices, edges we have not given, so we cannot know about the how many edges are there, right? So but we definitely know that it can be an even number, because sum of the degree uh, can be 2 into number of edges. So number of edges, if it is even or odd, so 2 into something, so it can be even, it will be even. So okay, and number of vertices of even degree in G is k. Okay, which of these value k, number of vertices of even degree. Okay, so k is even number of, actually number of vertices even degree. So okay,
If you can
okay,
explain enough, I mean, some basics of deriving all these kind of things. So, I mean, conceptually, we want to clear the concept.
okay, I'll explain you. Okay, so you know that number of uh, actually this question is we have to guess, we have to just guess about the things. Just what I can say, that sum of the degree, okay, I'm just telling the answer, sum of the degree of all the vertices in G is D. So you know that sum of the degree of all vertices can be 2 into some number of edges. Okay, so 2 into number of edges, and you know that 2 into number of edges can be even number. Okay, so by the even number, if and even number is, yeah, here is 42, 41, whatever. So by this way we can know that number of edges we can know, right? If
Okay.
2 into number of edges is there, we know that
Yeah.
40, it can be 42 or 41. So we know that number of edges, we can know that 42 into 2 divided by 42 to divided by 2 is 21. So 21 can be number of edges. It means that we have a 17 vertices and number of edges is 21. We know that.
Yes.
So but this is means by logical things and some kind of thing like, and we know that 17 is the number of vertices. Okay, so 7, it means that number of odd vertices and number of even vertices, if we add those vertices, 17 includes number of odd and number of even degree vertices, right? So, and we know, and we have to check that if it could be 9 or 10, right?
Yes.
And you know that odd degree vertices in any undirected graph, odd degree vertices, number of odd degree vertices cannot be odd. Do you know that means number of odd degree vertices can will be an even number, means number of in undirected graph, uh, means number of odd degree vertices should be even number. Means we can say even number of vertices will have uh, odd degree kind of, means odd degree vertices in the number kind of thing, it will be an even number always, it cannot be odd. So by this way you can get the answer, it can be 9 or 10.
Okay,
Means
sir.
these kind of things you have to know, means these things will come that odd degree vertices will be an even number in an undirected graph. So I am telling you the answer actually. I think you didn't know about these things, like even number of even number will be there for odd degree vertices. This is the theorem that odd degree vertices will have even number. Some even number will be there. Even number of odd degree vertices in an undirected graph. This is the theorem. So we can use these things. Means this kind of question generally we will we can do it by some logical or aptitude kind of thing, and by knowing some general graph theories theorem. By this way we can solve. Otherwise, we will use some some theorem, some direct theorem about graph theory.
Okay, sir. I'll explore further.
So did you understand, or just saying that yeah I understood?
Sir, fine.
Anybody
I mean,
else having this?
some of the degree will be always the even number because it is in 2m form. So from these options we can make out. But actually, I was looking for some basic kind of explanation in terms of the calculating all this. Okay, with this.
Yeah. Why I didn't give you the basic explanation? Because for this question we don't know about the the vertices and edges, and we have to assume something, because there is all the information was not given in this question, right? So we have to assume, so we have to take some assumption. That's why the basic theorem, by this theorem, hence applied this, like chaining kind of thing. So this kind of thing will not work here, because we have to assume all the information is not given. It's like the competitive question, in the competitive exam we do generally this kind of thing. So that kind of question, this is the kind of question, the competitive exam kind of. Yeah.
Hello, Rajat sir.
Yes.
So in the last video where we are calculating the longest path, so I didn't understand the uh, last quote, sir.
Last quote means?
So the code that sir have explained, so I have tried multiple times on collab
Okay.
notebook also.
Uh, okay. So everybody listen this problem, right? So anybody understood that code, or anybody wants to share something? Anybody uh, anybody wants to explain this code to us? Nobody. Okay. Everyone. All of you can see my screen.
Yes, sir.
Yes, sir.
So from while.
Okay. So can you explain us about this from starting? Can anybody explain us? Nobody. Okay. Huh. So what's your name?
So Divakar.
Divakar. Okay, Divakar.
So I can explain till before while.
Yes, yes. Yeah, please explain us.
So there is a list,
Okay,
adjacency list.
before this longest path. So what is our logic to calculate longest path? You know,
Yes, sir.
what do you understand that how we are calculating the longest path?
So where topological sorting.
Yeah, our logic is we are just calculating the longest path as maximum of longest path of any previous vertex plus one for the next vertex. Just we are just doing plus one, right? Uh, yeah, our logic is here 1 plus maximum of longest path from I to j from any vertex. We are uh, just adding one as a longest path. Means for 0 the longest path will be some 0, so for 2 it will be 1 because 0 plus 1 1. Okay, so this is our logic. We'll remove 0 and we will calculate longest path as 0 plus 1 1, and for 1 we will just add plus 1 also. If we remove 0 and if we remove, then we remove 1, so our longest path will be plus 1 and plus 1, it will be 2 for 0 and for 1 overall.
For 7 there are total 2 paths. Longest path, that is 4. Like total 4 edges are there from 0 as well as from 1.
Yes.
0 3 5 6 7 and 1 3 5 6 7. right, sir?
Zero, three. What you are saying?
So the longest path.
Zero.
So total number of edges are 4. 0 to 3, 3 to 5, 5 to 6, 6 to 7.
5, 5 to 6. Yes.
As well as the from 1 also, 1 to 3, 5, 3 to 5, 5 to 6, 6 to 7.
6 to 7. Yes.
Yes, sir. So I understand the concept, but I am unable to do coding.
Okay, okay. We'll do coding. We'll do coding. I'm
I've
just
tried multiple times.
okay. We'll see here. Okay, so explain us about the before while. Hello, Divakar. Hello, Divakar. Hello. Am I audible?
Yes, sir.
Oh, okay. Divakar, I think he lost.
Sorry, I get disconnected.
Okay, okay. Okay.
So in first for loop, we are using, sorry, we are using all the names of the stations or whatever it is. Like we are making as many as number of keys, we are making their values is equal to 0 in both of the integrity and L path. So in the second for loop, for you in alias dot keys, we are making value in degree, like value of, sorry, keys value is equal to v plus 1. And so in the third option, sorry sir, I am unable to explain the third part.
Okay, so what we are doing here, we are just making a queue, 0 degree as a queue. And for you in alias.keys, if in degree u is equal to 0. Okay, so yeah, actually for everyone, what we are doing here, for longest path, we know that for longest path we have to go through it by topological sorting, and we know that what we do in topological sorting, uh, first we will find the in degree vertices, and as we know that in the directed acyclic graph we have, surely we will have a one in degree vertices whose in degree will be 0, in degree vertices whose in degree will be 0. Okay, so here we are in the topological sort, we are just doing this. 0 degree is our queue, and what we are doing, we are just choosing whose in degree is 0. Means this is kind of thing like we are just inserting, we are just going through all the vertices, and we are checking whose in degree is 0. If its in degree is 0, then we will just add into the queue. It's like BFS. So if in degree is 0, we will add into the queue. What this is what we are doing here. Okay.
So it means there is a key whose value is not there in the values. So it means like there is a key which is not available in the values of the keys, that we can say as an in degree, whose in degree is 0.
Actually, if you see here, for u in a list dot keys in second for loop, u in a list dot keys, and for v in a list dot u whatever it is. So we are just calculating here in degree. Here we are just calculating the in degree of the vertices. And if it is for any vertices, we are just calculating some numbers. And if it is 0, then we are first we are just updating the values of the vertices, some integers value. We are just updating some integers value of the vertices in this for loop. And here in this for loop, we are just checking that that updated value, if for updated value, if it is 0 or not, for any kind of thing, for any vertices, if it is 0 or not, we are just checking, and we are only inserting those values. Already we marked all the vertices in degree u. That is kind of that we have a dictionary. So we are just putting it as a 0 0 0. We are marking as a 0. Okay, some keys and zeros. So, and we are just updating the zeros into 1 2 3. And here what we are doing, just uh, we are checking the value of the dictionary, that some keys whose value is 0. I'm just checking these things here. And if we are finding any keys whose value is 0, then we are just adding into the queue that keys. Actually, in that key value, we are just inserting. Key is our vertex number. So that's what we are doing. And you know that this is what we do in topological sort. We have to find out the vertex whose in degree is 0. So that's what we are finding out. Whose in degree is 0, we are just inserting it into the queue. And it's like BFS. And here in the while loop, we are checking queue is empty or not. If queue is empty, then we are done. If it in the BFS also, we have done the same way, that if queue is empty, then we are done. If queue is not empty, then we have to traverse. So if queue is not empty, means we have, and definitely in directed acyclic graph, queue will not be empty for initial vertex. There will be a vertex. So what we are doing, some 0 degree, that we are just uh, deleting it. And the same way in the topological sort we do na, that we will delete those vertices 0, or mean that in degree vertices we delete it. So that's what we are doing here. And we are just decrementing its in degree also. We are just deleting, because you know that for every next, that suppose 0 is a vertex, and 2, suppose we have deleted 0. So all the vertices that are connected with 0, those in degree will automatically will decrease, because we have deleted 0 vertices. That's why we are decrementing 0, decrementing 1. uh, so is it correct? understood? Hello?
So if you just code this part only, I can.
Yeah, this part.
Yes, sir. From while.
So that's what I am doing. So uh, can we by this means, if we will do together, then we can understand in a better way. Okay, so everyone who can understand will tell us. Okay, so what you are thinking about this, Divakar? What you are thinking about this? So from definition part to this part, have all of you understood, right?
So in while loop, we are using 0-degree vertex and
Here what so you just uh, do it with we will do it together, then we'll understand. Okay, so in the while loop, what we are checking, that queue is empty or not, because in the queue section we have some n degree as a 0 vertex. We have some vertex in a queue, so we want to check if there is a vertex or not. If there is no vertex, why would we check? Means we are done. Okay, so is it good? It's like BFS.
yes.
And the same thing what we do in the topological sort, that we are deleting that in degree vertices. So is it good?
So when we are taking like if we take vertex 0, after that we are deleting 0
Because
and
that's what
taking.
we do right now.
Yes, sir.
That's what we do in the topological sort, that we have to delete that in degree 0 vertices.
So why we are doing in degree j minus 1 and in degree k minus 1?
Why we are doing j minus 1, right? Because 0 has because you know that how to make it.
So
You
value
know,
of in degree j is already 0.
yeah, that's what I am also thinking, that it is already 0.
So first vertex it is already 0. After that, if we are taking any other vertex.
Okay, okay, suppose we are just doing it, that we are deleting 0, and here we are doing 0 minus 1 minus 1. Okay,
Yes, sir.
okay, so and here we, that's suppose we are not able to understand this, that why it's minus 1, but definitely it will be, because it will help us to uh, make it to get out of the loop. But suppose for k in a list j, that is adjacency list, that is the list of the j, that 0 connected element, that 0 connected vertices, we have to reduce it, right? We have to reduce it, because every 0th connected vertices, we have to reduce the in degree also, right? Because we are deleting 0, so we have to reduce the in degree also. So it is good.
Yes, sir.
So that's why we are just deleting k minus 1, means we are just reducing 1 minus, for because we have deleted that 0 or something. That's why we are,
So for k in a list j, it will use 2, 3, and 4 every time, like for loop. So a list j means a
2
list of
3,
0.
yeah, so 2 3 4, for 2 3 4, so what it can do, for 2 it will
So
delete,
first it will take 2, after
okay,
that 3, and after that 4.
4. So
So
for all these it reduce the degree.
okay,
Yeah, so that's what we have to do, right? We have to delete all these degrees, we have to reduce one. So that's
okay,
what
sir.
it is doing. Yes, it is doing, right? And here the longest path, it is calculating the longest path. Okay, longest path of k means longest path of 2 3 and 4 along with this. So is it good? Means longest path of k plus longest path of j plus 1, and the same means longest path of j means
So both are
previously.
same, 1, 1.
So
Longest
if
path
it
k
if
and longest
yeah,
path
if
j
it is
plus 1.
same, then it can take any one, but it, the algorithm is this thing, right? Longest path k, or maximum of longest path k, or longest path j plus 1. This is the algorithm. So it is calculating the longest path of 2 3 and 4 in this for loop actually. And the same way it is checking that any in degree vertices of the k, means in degree vertices, suppose we have reduced the in degree vertices by 1. So we are checking it that any in degree vertices is 0 or not, because ultimately we have to check in the queue also that any in degree vertices is 0 or not. If it is 0, then we are adding into the queue also, because we have to go through the in degree vertices, those who has in degree vertices whose in degree is 0. So we have to check all those vertices. That's why here we are checking it. If it is 0, then we are adding into the queue. And the same way, and then again, for this two, means for this for loop, it will after run 2 3 4, and then it will again check that if queue is empty or not, the same way it will does. So it is working fine, I think. So have you understood the concept?
Yes, sir. So if we'll take 2 only in the end, if loop, sorry, if condition, the degree
uh,
of 2 is 0.
okay, if degree of 2, suppose it was 1 earlier, so we have reduced 1 minus 1 is equal to 0. So uh, here we are
So
checking.
we will reduce the in degree of 2.
Yeah,
I'm
here,
asking
yes,
here.
here in
So
degree of k.
not in the while loop, right, sir? Not in the third line of while.
No.
So in the fifth line, we will reduce the value of 2.
Actually, if we remove this line, suppose if we will remove in degree of j is equal to in degree of j minus 1, I don't think it would affect our program, right?
So
Because
this is an extra line.
I think it will not affect our program.
So that's why I'm asking.
Yeah, because what we are doing, we are just picking up the element from the queue, and we are just reducing its in degree, right? And you know that if there is an element in queue, it means that it has in degree 0, because otherwise it won't be there in the queue. So we every time we are just reducing it at 0 minus 1 minus 1, and we are not using these lines because we are not using, right? We are not doing anything with this j. We are just doing with whatever the list, whatever the connected vertices of it. So if we will comment these lines, that then also the code will work. Yeah.
So after that, if condition
Anyone?
we are adding also value of k in the queue.
Yeah, we are
So
adding,
sorry,
right?
key k means we are adding again two in.
Yes, we are adding two. If we find out that two has in degree 0, then we are adding it into the queue also. And that's what we have to do, right? We have ultimately we have
So
to.
but there are already 2, 3, and 4 in the queue, and we are again adding
No,
2.
we do not have 2, 3, 4 in the queue. We only have 0 in the queue. Okay, we already here what we have done, that we have checked all these things. Okay,
So
so
after this complete for loop, we are adding 2, 3, and 4, right?
yes, after this, no, not the 2, 3, 4, only which have a in degree 0 from 2,
Okay.
3, and 4.
So we are
And
adding 2 and 4 only.
if we have a 2 and 4 whose in degree is 0, then
Because
we are only adding 2 and 4, not 3. And we
3,
have,
3, 3 also have a in degree 0 after that, maybe.
if suppose if it has, we are reducing it. Okay, if we are reducing it because we are just reducing the size, sorry, the in degree. So if it's in degree is 0, then we will insert into the queue. If it is not, then we will not insert it.
So after that, we will explore 2
Yes,
in the while loop.
because yeah, here we only add those vertices whose in degree was q, whose in degree was
So
0.
after in degree 0, we are checking the condition in the while loop. The second
Yes,
line, when we are subtracting -1, so we are making uh, in degree -1 for that vertex,
yes,
I think.
yes. So what this program does, that it is just adding, first it is just adding those vertices whose in degree is 0. It is adding into the queue. Suppose 2 and 1 is 0, and 1 is the one has initially 0 as a in degree, so it is adding into the queue. And then after it is checking that in the while section that queue is empty or not. If it is not empty, then it is just going through all the vertices that are connected with 0. Suppose it is picking up 0 and it is connected with, and the sub and in degree is connected with, sorry, vertex is connected as 2, 3, 4 from 0. So what it is doing, that for 2 it is just removing, because it has been removed, 0 has been removed, so it is reducing the in degree of 2, 3, and 4. And then it is checking also, it is parallelly, it is checking and parallelly calculating the longest path of that 2, 3, 4. If any one of them 2, 3, 4 is has in degree 0, then it will add into the queue. And the next time that it will go to 1, then after 2, 3, or 4, whatever it will added in the queue, it will go through from these while loops. So that's what it is doing.
So in L path K, we are using degrees also.
No, uh, longest path,
Yes, sixth line in the while loop.
so I think that you have understood the longest path, right? So
Yes,
that's
sir.
what the logic, right? The longest path. So that's what the longest path is, calculating the longest path. Means by this way, the longest path we have calculated, it is using the same thing.
So for example, if there is a programming exam, how do we like do it from scratch? We have to learn it.
No, you don't need to learn. Actually, you have to do it by your own and by practicing much. I know this is difficult. That's why I mentioned in the first live session that in the graph section you will face difficulty. Previous batch also faced their difficulty, and I agree that it is difficult to code, right? Means all these we are thinking and we are discussing, it is difficult to code, but but you have to learn
Because I
all these coding.
understand like two multiple concepts in the graphs, but there are already given codes in the slides also, in the Google Collab slides. So that I can solve the graded assignment questions.
So yeah, that's what I can suggest all of you, that solve as many question on the graph. Start with start with 2 3 4 lines of code, or some 5 lines, or some 10 lines of code related to the graph theory, not with the other because graph question is different from other programming. We have to think and we have to code, and it is little bit difficult, I know. And we have to do, because we have to pass the exam and we have to learn also, so we have to do it. So try to code a short simple example, then then proceed to the these kind of question, then only you can solve it. If you will directly approach to this kind of question to code, then there will be a problem. So anybody
So what type of
else?
question do we expect in quiz 1?
Quiz 1 will be generally objective type of question we will have, and
The time complexity questions also are
means
there.
that all the graded and practice assignment, those similar kind of question, same kind of question. We have covered all type of question in graded and practice, so practice all these question from 1 to 4. Question level will be same and topic will be also same. So if you have solved all the graded and practice assignment by your own, then you definitely you can solve those question also. It will be related to programming, some programming, snippet programming, some time complexity, okay, some graph theory question.
So in the
Not
graded assignment question, I have to use multiple times my console to extract the more information. What what type of question will means what type of information I am getting from the question,
sorry, I
means the
didn't get
code.
you. Means what do you want? I didn't get you.
So for example, there is a question and there
Okay.
is something written in code,
Okay.
in Python code, and I am not able to understand while reading it.
Okay.
So I just write it on the console and run it.
Okay.
After that, I am able to understand the concept of that.
Okay. Okay. Okay.
So in the paper, we are not able to do that, right? So
You definitely, there will not be any console. So this kind of thing you can do it by pen and paper, that yeah, this is what
I have
the
tried
programming.
the sorry, I have tried the selection sort. There is a question week to graded assignment, in which part the selection sort the list. So
Oh
I have, when I used pen and paper, I have get 7, but the
yes.
answer is 5.
Yes. So because I remember that question. So because uh, at the fifth step it was sorting all the element, that's why the fifth was the answer. Actually, I think you have missed some step, that's why you are getting 7. But after the fifth step, it has sorted all the elements. That's why the fifth was answer.
Okay, sir.
Want to take some feedback about the graph this week 4 actually. So what are you facing? Some means what
If
are your
there is
feedbacks?
side by side coding also, we will understand better in the graphs.
I'm asking all of you that what you are facing means, uh, are you facing any difficulty understanding the concept of graph theory, this graph, or is it different from previous lecture like 1 2 3, or is it little bit difficult? Generally, what do you think?
Because all the graph theory we have studied also in maths 1 in week 10 and 11 and 12 also.
Sir, I'm the theory part of it is okay, sir. Like we can understand it because we have already learned it in Maths 1. But the
Okay.
coding part is really very difficult, sir. That is
Yes,
what
yes.
I'm
Yeah,
finding it
yeah.
very hard
Yes,
to do.
yes, I
I'm not
understand.
able to get all the concept when sir explains it, like even. But when it comes to me sitting and coding, I'm not able to even
Yes, yes.
even the algorithm part of it. I'm finding it very difficult. Even
At
PPS on my own, I really found it very difficult. I was not able to solve. Uh, I was able to solve only one out of the three
yeah,
PPS.
actually, it is difficult. That's why you are facing difficulty. It is difficult. That's why yeah, it is difficult. So it is not easy. I am saying it is difficult. I have mentioned earlier that graph will be a little bit difficult. Rest of all will be fine, but that's what you can do. You all of can do that. You can practice
So
short graph question.
which website is better for practicing
No,
basic
practicing
questions
basic.
of graphs?
You have to find on the internet that no website is there for just to actually HackerRank. There will be a separate section for graph theory question. So but try there for easy, because they have something labeling like easy, difficult, and medium. So try with the easy one, and then after we will, because here we have some medium kind of question. Medium, you can see that it is not as much difficult. Just we are, what we are doing now, that we are just using BFS and DFS again and again in the graded assignment also, and the PPS also. We have used graph, BFS and DFS algorithms in every question. Like we are just visiting cities, so whenever visited comes, you just think about that BFS and DFS would be there, because we are visiting anything. So try to solve easy question, then try to solve these medium kind of question. We have a medium labeling question here, not the easy one. And if you haven't gone through any kind of graph question, then it will be you will face difficulty while solving these graph problems. But it is medium problem.
Because now is that sir, we couldn't find time even to complete the GRPS on time, sir. Like
Okay. Why you
working
have
on.
taken many other courses?
No,
Or
sir.
you,
Only 2 courses I've taken. Like
it means you are working anywhere?
I have
yeah.
taken 4 courses.
Oh, okay.
So I am not able to extract time for the coding part.
What's your name?
Divakar.
Okay, okay, okay. For working, yeah, it is for working professional, it is uh, very difficult to complete all the assignment while solving all the things, and it is difficult also. And you know that PDSA is one of the difficult courses from this.
I try to do the live coding problems, like I try to complete them as much as possible.
Huh.
But apart from that, outside the given course content, I will not be able to. It's doubtful that I will be able to. Given the difficulty of the GRPS, it takes me nearly all the days of the week, like 5 to 6 days to complete just the GRPA. I make
Okay.
sure I
Is it
start it as early as possible.
okay? Is it related
Till,
to this week, week 4, or
yeah,
uh,
this week
oh, okay,
especially.
this week, especially this week. Yeah, actually, this week is difficult. I think that's why. Uh, okay, let me check uh, what we have in other week.
Week 3 was okay, sir. I was able to do that. Week 3, week 2, and all. It was
Week
not
2
this hard. Like, it doesn't, like, I'm totally drained with all this.
Okay, actually, bad news for all of you that after this week 4, we all have all the weeks will be little bit difficult. Week 5 also related to the graph. Okay, week 6, not the week 6. Week 6 is a heap kind of thing, heap structure, queue, heap. But week 7 also that Huffman coding, some balance search tree, means tree, it is related to trees. So week 8, week 9 is like dynamic programming, string matching. So all these week will be from now onwards. Week 4, there will be you can see that there will be uh, difficulty increasing, some kind of, means step by step. You will see in coming weeks that week 4 and week 5 is totally related to graph. So they don't means do not feel that I am not getting it perfectly, but try to solve as much as you can. Week 4 and week 5 is uh, really a difficult one. It is related to the graph, purely graph related. Yeah, try to solve all the things step by step.
So it's the only way that we have to solve patiently. That's the way, right? And
Yes,
like
solve with easy
as much
question.
as possible.
Solve
Okay.
with easy, means start with
Okay.
easy question and then try to these question. I'm not saying that do not try the graded assignment, means after all you have to solve graded assignment within time also. That's what we can do.
Okay, sir.
Any other thing, or shall we close? We have a tomorrow session also, a Thursday. Shall we close?
Yes, sir.
Okay. Thank you.
Thank you, sir.
Yeah. Thanks to everyone. Yeah, you can ask Snehil. PPA week 3 we will solve in the revision session. Keep it with you. We will solve it in the revision. Is it fine? Or maybe you can ask in the discourse also. If anything, we will provide you the solution also. You can ask on the discourse also. Maybe it's better to ask on the discourse. Okay, ask me. Okay, whatever. Yeah, okay.
Sir, I was using for there is a self.hash table, which is a list in the class that is given in the PPA. Hello.
Yeah. Week 3 PPA 2, right?
Yeah.
Okay, let get yeah. Uh, I'll get back to you. Okay,
Yes, sir.
I'm just seeing that.
Yes, sir.
If if anybody wants to leave, they can leave. Okay. Yeah, you can tell us. Yeah, what is your what's your problem?
So I was using a simple statement if that if none in self dot hash table and then something. So that was just to check if uh, the hash table was full or not. Am I audible? So this statement for some reason doesn't seem to work inside the if clause alone because it throws an error saying integer type error, integer is not subscriptable. Now, if I write the same code as j equals to none in self dot hash table and print j, then j shows the right value, true or false, accordingly.
And previously, what you were saying, if with
I just use the same statement, none in self dot hash table inside if.
Oh, okay.
Inside if it doesn't work, it throws a type error. Outside if I assign a random variable to it, then it works. But if I use the variable again inside the same if statement, it shows the same error, type error.
uh, uh, means you are earlier you were checking, means earlier means where when you are getting error. Okay, so earlier you were checking none in the if statement, that self dot has none with the self dot has, you are checking none.
Yes, sir.
Checking in the self dot has. Okay, so it
Yes,
was
sir.
throwing an error.
Yeah.
And if you are doing with the j and checking any none value,
Yeah.
that it was working.
Yeah, it works fine. It stores the Boolean answer inside j. So when I print j, it accordingly gives me a true or false if there is a none inside hash table or not. However, if I again use this new variable j inside the same if loop, instead of writing if none in hash self dot hash table, I just write if j. It again throws me the same error, that type error, that it is not subscriptable. Integer type is not subscriptable.
Type error usually comes when none is you know that none is a keyword, right? And if it is taking this keyword as a word kind of thing, then it will show something type error, it kind type error kind of thing. If uh, if none, so can we use this as this statement as a if none something kind of thing? Because we are comparing something in the if statement, we are comparing something, and we are comparing none to uh, we are just comparing none to from the hash table. uh, so uh, you know that none, uh, definitely it is what I think, it is not taking none as a true or false some kind of thing, like 0 or
But
1 kind of thing. It is not comparing it. The we whenever we compare two things, we that comparison should be on the same level, right? And uh, and none and self dot has something, there will be a some he it will be kind of thing in the self dot in the hash table, none will be pointing as a 0 1 kind of thing, 0 or
but that
something.
should throw an error for when I'm initializing it as a variable too, right? When I say j equals to none in hash table, it should still throw the same error.
Because when j equals none, right, you are checking j equals none.
No, I'm saying j is equal to an expression none in hash table. Like we use for I in list, that kind of. If none is in list, then it should give me a true. If it's not in the list, then it should give me false. I'll write it in the chat too.
Better to write in chat. It's better to write it on the discourse, right? I'll get back to you on the discourse, means after this meeting, means after 10 or something 11 in the night, I'll get back to you.
Okay, so I'll make another thread with
yes, make
PPA2
another
and
thread. I'll get back to you on the discourse.
Should I tag you in it, sir?
No, nothing to tag, just to write. I'll open and week I know that week 3 PPA2. So
okay, sir.
Yeah, I'll get back to you on the means after this meeting, 10 or 11 something.
Yes, sir. Okay, thank you, sir.
It will be fine.
Thank you, sir.
Yeah, thanks. Okay, everyone. Thanks.